Hello, my name is Alan Journet. I am, as you can see, co-facilitator of Southern Oregon Climate Action Now. My charge for this presentation is to introduce you to climate projections for the Rogue Valley with a watery focus. So let's start the ball rolling by looking at what we mean by the Rogue Valley. I am going to be focusing on the lower Rogue and the middle Rogue. As you can see here, the outline of the Rogue Valley takes us, or Rogue Basin takes us from the coast up to Crater Lake and takes us actually down into just over the rim of California and back to Gold Beach. I'm going to focus particularly on the lower Rogue and the middle Rogue Basin. The lower Rogue and the middle Rogue are essentially separated by Grants Pass, and you can see Medford here is solidly in the middle Rogue. If we go further up the Rogue River, we're in the upper Rogue, and that will take us up as far as Crater Lake. Let's start by looking at what kind of projections I'm going to be talking about. My focus will be on the projections that were developed by the United States Geological Survey as a consequence of the Intergovernmental Panel on Climate Change projection models that came out with the Assessment Report 5, which was dated 2013-2014. So let's have a quick look at what these mean. The RCP, Representative Concentration Pathway 2.6, refers to what would happen if we ceased in greenhouse gas emissions immediately now. The concentration phrase in RCP, Representative Concentration Pathway, refers to the concentration of greenhouse gases in the atmosphere as measured in terms of their carbon dioxide equivalent. The RCP 8.5 refers to, when it was first developed, it was described as the worst case scenario because it's based on the assumption of a continued ongoing acceleration of greenhouse gas emissions resulting from ongoing accelerated fossil fuel use. It was initially designated as the worst case scenario because it was thought we wouldn't possibly be following that trajectory. Well, it turns out, unfortunately, when we look at the data, that is exactly the trajectory we're on. So that has become known as the business as usual trajectory. We also have intermediate trajectories, the ambitious reductions trajectory, RCP 4.5. That assumes that we take some really serious steps to change the trajectory from that business as usual trajectory. And then there's the less ambitious reduction trajectory, RCP 6.0. And you can see on the chart on the right that an RCP 2.6 would result inevitably in an increase in about 1 degree centigrade, which is about 1.8 degrees Fahrenheit in temperature. And an 8.5 RCP would result in about just a little over a 4 degree centigrade increase in global temperature, which amounts to about 7.6 degrees Fahrenheit. Let's look at these USGS projections. Notice the baseline for these projections is 1981 to 2010. So that's the baseline for consideration of changes, and it's the average over that period. The red line refers to that RCP 8.5 scenario, business as usual scenario I just mentioned. And I will remind you that the lower Rogue is from Grants Pass on down to the coast. The RCP 8.5 increase is projected to be a little over 8 degrees Fahrenheit by the end of the century. Meanwhile, the RCP 4.5 increase is about 4.5 degrees Fahrenheit. Let's come up from Grants Pass through the middle Rogue, and we'll see again the RCP 8.5 increase is now a little over 9. We get a general trend that as we go from the coast inland, projections suggest more serious changes. And this is particularly true with temperature. The RCP 4.5 now is at 5 degrees Fahrenheit by 2100 for the middle rogue. Let's look at this in terms of the seasons. The historical winter temperature was about 40, just a little under 42. Spring, 51, fall, 54.5, and then summer, not surprisingly, a bit higher, 66. So let's look at what the USGS suggests, according to the 8.5 RCP, will happen by the last quarter of the century. And what we find is that by the end of the century, winter will see 6 2/3 degrees Fahrenheit increase, spring about 6 and fall about 7.94, with a summer increase of about 8.79. For the middle rogue, on the other hand, winter is about 40, summer 60, nearly 67, spring nearly 50, and fall about 53. The increase for winter will be something like 6.9, spring 6.39, fall 8.29, and summer maybe 9.5 degrees Fahrenheit warmer by the end of the century. Let's now turn to precipitation. Again, remember the baseline is 1981 to 2010. That's the average baseline, the baseline average. And again, remember we're going down below Grants Pass for the lower rogue. By the end of the century, we're expecting to see a decrease of about 0.25 inches per month. And for RCP 4.5, about minus 0.19 inches per month. Let's go to the middle rogue now. Again, remember this is Grants Pass and through the middle part of the river above. RCP 8.5 down 0.1 of an inch, and RCP 4.5 down 0.02 inches. And we'll now look at the seasonal pattern for the lower rogue. The lower rogue, winter nearly 33 inches, spring 18, summer 2.7, and fall 17.5. And you can see it depicted there, a typical pattern that occurs with the Mediterranean climate, where winters are much wetter than summers. What's the change likely to be by the end of the century down below Grants Pass on average? And the answer is winter, an increase of some 2.5 inches, spring, a decrease of maybe 3.5, summer, a decrease of maybe half an inch, and for fall, a decrease of about 0.1 of an inch. For the middle rogue, historically, winter was 12.5 inches. You can see much lower than the lower rogue with its maritime climate. Spring, little under 7.5 inches. Summer, again, Mediterranean climate, very low, 1.7, maybe about 1 3/4 inches, and fall a little over 7. By the end of the century, what we're expecting is winter will be up 1.74 or so inches, with spring down a little over 1.5, summer down 0.27, about 1/4 of an inch, and fall down a little over 1 1/4 inches. Another trend that we're expecting in terms of precipitation is one that has been historically evident, and that is a trend in heavy precipitation events. What you see here is during the 1910s, 20s, and 30s, there was a relatively low number of days with very heavy precipitation. But as we move forward through the 60s, 70s, 80s, and 2000s, and so forth, an increasing number of days with extreme heavy precipitation. This is a pattern that we expect to continue, as depicted here. Notice dark orange is the high emission scenario. Think of that RCP 8.5. And the yellow is the low emission scenario. Think of RCP 4.5. And what you can see is that the light precipitation events are likely to decrease. These are the kinds of precipitation events that replenish soil moisture and do so very effectively. Whereas with high emissions scenario and with, actually with both high and low, what we're going to get is an increase in the number of heavy downpour days. This kind of precipitation doesn't replenish soil moisture, but it results in flooding, soil erosion, and landslides. Flooding potential with rising ocean levels, those along the coast are likely to experience higher tide and storm flooding. Meanwhile, we're likely to see earlier spring rainfall in the mountains, which could lead to quicker snowmelt and potential flash floods, particularly in riverbeds. The warmer air will increase evaporation, especially over the oceans, and we're expected to find across the planet, and we are indeed seeing, an increase in humidity, as noted here, has already increased 5 to 10%. That rising warmer air produces higher rainfall events as it cools. That releases energy into the surrounding atmosphere, and again, that will increase the severity of storms. What we can see here is an increase in one-day precipitation events from 1910 to 2020. You can see that what we have experienced is an increase in those one-day precipitation events. What we're seeing is a tendency for precipitation to fall at lower elevations as rain rather than higher elevations as snow. That becomes a real problem for us in the Rogue Basin and throughout the West, because we have been using that high elevation snowpack as our reservoir for summer and fall irrigation and drinking water. Crater Lake, for example, since it was invented back in the 1930s, has experienced a consistent drop in snowpack. You can see quite variable over that period of time, but the trend is one clearly of a decrease in snowpack accumulation. Let's now look at snow water equivalent as it appears in, firstly, the lower Rogue, that area below Grants Pass, averaging down to the coast. You can see that we have experienced a reduction in snow water equivalent since about the 1960s. The history has shown that decrease happening. And I should point out that snow water equivalent is what really is ecologically important, because we're not now measuring just the depth of snow, but the amount of water in that snow. That's what is important to agriculture and forestry and our natural ecosystems. What we have seen, or what we are expected to see by the end of the century, is a drop in the snow water equivalent of about 0.45 inches. And you can see, if we come back here, that the total water equivalent is only about 0.5 inches. So you can see, according to that RCP 8.5, the amount of water in our snowpack is going to dwindle substantially. If we don't follow that business as usual scenario, but we're a bit smarter, then the drop in snow water equivalent is going to be less. So we're not going to be quite so badly off. Let's come up above Grants Pass now to the middle road. And again, you can see that historically the snowpack, snow water equivalent, has been dropping from a peak of around 0.4 inches. And again, what we can see, according to the RCP 8.5 scenario, by the end of the century, that will drop by 0.34, which is a substantial proportion of that precipitation, or that snow water equivalent in our snow. According to the RCP 4.5 scenario, not quite so severe, but not much different. Let's look at that in terms of seasons. Well, of course, winter is going to be the most profoundly important when we're looking at snow water equivalent. And so what we see is historically, for the lower road, winter precipitation was a little over an inch and is expected to drop by most of that, by 1.12 out of the 1.16 inches. For spring and summer and fall, yes, indeed, there has been historically snowfall during that period of the baseline period, 1980 to 2010. And yes, indeed, those amounts of precipitation are going to drop also. So by the end of the century, we're expecting to see very, very little snow water equivalent in the lower Rogue part of the basin. In the middle Rogue, winter was around just a bit under an inch, spring maybe a third of an inch, and fall 0.02 of an inch, summer none. By the end of the century, most of that winter snow water equivalent accumulation will have disappeared, spring almost all, and fall totally. And of course, summer being zero anyway, the drop from that is zero. The consequence of these sequence of events is going to be a change in the projected timing of the peak runoff in our streams and the amount of runoff in our streams. So with warming and a loss of snowpack, what we're likely to see is the runoff peaking much earlier and much lower. That means, of course, less water flowing down our rivers, creeks and rivers. And some parts of the western United States are likely to see this peak shifting not just to earlier in the year, but even to late November, December the previous year. So you can see a marked shift in the peak of runoff of our rivers. Notice that not only is the peak earlier, but it's lower. And also that as we go into July, August, and September, the time of year when our agricultural systems really need the water coming down those irrigation ditches, the amount of precipitate, the amount of water coming down out of the mountains is going to be way lower, a real problem for our agricultural systems. Late summer and runoff much lower. Let's look at what all of this means to soil moisture, and I'm first going to talk about what's called the evaporative deficit. So what I want you to imagine is that our soils contain about 3 inches of water. Now, what we know is that when the sun shines, water evaporates. The temperature results in water evaporation. So here's our sun causing evaporation. Supposing that the effect of the sunlight, the heat on the soil moisture is to evaporate 2 inches of that soil moisture, then what you can imagine, I think, relatively easily is there's going to be 1 inch of soil moisture left. However, if we only start with 1 inch of moisture in our soil, and again we have the same 2 inches of evaporation, what you can imagine is there's going to be basically no soil moisture left. What we have is what's called an evaporative deficit, and I think you can probably very quickly imagine that 1 minus 2 equals an evaporative deficit of minus 1 inch. So let's look at soil moisture storage trends and projections in, firstly, the lower Rogue. Well, again, what we can see is starting in about the 1960s, the soil moisture storage has been dropping. According to these projections, by the end of the century, the RCP 8.5 scenario is anticipated to result in a drop in soil moisture of about 0.38 of an inch. The RCP 4.5, you can see, is just about half as severe in terms of the drop in soil moisture that it is likely to impose. Now, let's look at the change, and I've indicated the zero line here. That's the baseline 1981 to 2010. What we see is that the RCP 8.5 is going to lead in the middle Rogue to a loss of about 0.46 of an inch, about half an inch less water in our soils. And with RCP 4.5, again, something like half of that loss. Let's look at that seasonally. Winter, the soil moisture averages historically about a little over 4.5. Spring, a little over 4. Summer, very low anyway, you can see that. And fall, 2.38. What are the changes likely to be? Well, winter is likely to drop a little. Remember, winters are going to be a little wetter. Spring drops substantially more. Now, summer doesn't drop as much as spring, but look at the amount of drop compared to what the historical average is. It's about 50% or more reduction in soil moisture. And then fall, again, substantial drop, but since fall soil moisture is a little higher, not quite so profoundly important. Let's come up, upstream of Grants Pass again, remember. Winter, the average is about 4.5, spring 3 2/3, summer under half an inch, and fall 1 1/3 inches. Into the future, winter again will drop somewhat. Spring will drop a little more, but summer, notice, it drops 0.23 inches from 0.32. That's about a 2/3% drop in soil moisture during the summer. And fall, not quite as great as in summer, but since fall is a bit higher in soil moisture historically, the impact is not quite so profound. But the important point to note here is the drop in soil moisture is really important during the very seasons of the year when our crops are growing, when our natural systems are experiencing their summer and fall growth. It's important for us to appreciate the overall curiosity of our Rogue Basin climate. It's an attribute which is typical of the Western United States, but here we are looking at Jackson County's century average precipitation in inches. And most people who've lived here any length of time are familiar with this. And what we experience is what's called a winter wet, summer dry climate. And you can see this as we look at the average precipitation in inches over the 20th century during the course of the year. This graph is called a climograph. Most people who live here don't realize how unusual this is. I've now imposed on that the temperature conditions. So you can see what we have is everybody knows this, summer hot, winter cool climate, but this is the point that's really important to us today, this winter wet, summer dry climate. That is very unusual. It's called a Mediterranean climate. It is very different from the rest of the United States, and I'm depicting here Louisiana, and you can see the second one down here is Boulder, Colorado, and New York. What we can see is in other parts of the United States, we don't have this rather unusual climate. We have situations where precipitation is pretty much regular throughout the year. Maybe it's a high in spring, maybe it's a high in spring and fall, but this particular Mediterranean climate is very unusual. It actually occurs across the planet in 6 places. The European Mediterranean, hence the name, both Southwest and Southeastern Australia, the South African Western Cape area, and Western South Australia, South America, and Western North America. So these are the 6 places, and this is us here, obviously Western North America. It's a very unusual climate. It results in certain characteristics. Historically, during late summer, the soil and the vegetation dry out. That results in an increased fire risk during summer and fall. Forest fires, vegetation fires are frequent where we are there, of course. Forest fires, in fact, where we live in the dry forests of Southern Oregon, historically, what's called the fire return interval occurred on average once every less than 10 years. And that means any given place in the dry forest system, that's the ponderosa pine oak systems of this part of the country, any given place is likely to have experienced a fire more often than once every 10 years. The result of all this is our vegetation is fire prone, fire adapted, and fire dependent. Our forests are dependent on the returning of fire. This is the case for the dry forests with which we are familiar, ponderosa pine, oak, madrone kinds of forests. So let's ask an interesting final question. Where in the world is the Medford area likely to be equal to in 2050 and 2100? And so let's first, and I'm talking about particularly the summers. This is the period that's very important to us in terms of our ecology. So Medford, where we live now, Medford area, is likely to be equivalent to Reading in terms of our summer climate by mid-century. By the end of the century, we're likely to be equivalent to the climate in Delano, which is, in case you're not clear where Delano is, it's right near Bakersfield. That's the climate that we are likely to be experiencing in our summers by the end of the century if we follow the business as usual representative concentration pathway 8.5 scenario. And that concludes my presentation. Thank you very much for your attention and good night.